Log on, tune in, find out. Another good idea from Cambridge.
Is Mareike Fischer, who's a postdoc in Vienna, and she's going to tell us about how many characters are needed to reconstruct a true tree.
Yes. Some of you may recognize this topic. That's why I called it Revisiting the Question, because actually I talked about the same topic already in 2007, and now I'll tell you what progress has been made in the meantime. Now this is joint work with Marta Casaneas, who unfortunately cannot be here today because, fortunately, she just had her third baby, so she's at home busy. Okay, well, what is the problem? Well, in phylogenetics, we are oftentimes given an alignment of data, for instance, of DNA data in this example, and we want to reconstruct sort of the true tree, so we want to know, given the data, how are the species underlying the data, how are they related? And well, there are various solutions to this problem. I represent them here with my cartoons, which might be known to some of you. So this is my friend Miss Parsimony, standing for the parsimony method, but we could also apply maximum likelihood, represented by Mr. Likelihood here, or we could use, for instance, distance-based methods, represented by Miss Distance-based here. And oftentimes we do this and we come to some results, and sometimes they don't coincide, and we have criticized all these methods in the past because of that. But the problem is it really just due to the method that we maybe get something we were not expecting, or do we maybe not have enough data? So I think if you hear biologists talking at phylogenetics conferences, you always hear the sentence at some stage, we need more data. So the question is our alignment long enough for reliable reconstruction? Okay, how much data do we need? Some previous approaches have been made to answer this question. For instance, Churchill, von Heesler, and Navidi in 1992 already investigated a 4-taxon scenario where they had a tree with an internal branch and 4 pending branches that were of the same length each. So they observed that the probability of reconstructing the true tree increases with the length of the interior edge. Okay, that's, I think, easy to see, because if you sort of have this edge very, very short, tending to 0, then the possible trees on 4 taxa, they look like very much alike. Then you have more or less a star tree scenario. So this is what they observed. As the interior edge gets longer, the reconstruction probability increases. And not surprisingly, also if you have more characters, so if your alignment gets longer, also you can improve the reconstruction probability faster. So Ziheng Yang looked at a similar scenario, also for taxa, but he kept the internal edge fixed at 5% of the total branch length in the tree. And he looked at 5 different tree shapes then, some of which look really familiar. For instance, he observed that in this so-called Ferris zone, where you have 2 short branches on one clade and 2 long branches on the other clade, their parsimony sort of outperforms likelihood. Also in the Felsenstein zone, where parsimony is statistically not consistent, maximum likelihood does better. But in the scenario that we will look at also today, and which was also the one that was investigated in the previous paper I just showed you, where the 4 pending branches all have the same length, Ziheng Yang basically observed that the optimal length for the interior edge ranges between 0.015 and 0.025. Okay, what does that tell us? Well, unfortunately, all these approaches mentioned so far were just based on simulations. So, so this number basically, as I said before, it's fixed at 5% of the total tree length, so gives you some information, but it's just based on simulations. It's not an exact result because it's not done analytically. So what was still needed at the time was a mathematical analysis of the influence of the branch lengths on the tree reconstruction. And a first approach was made by Mike Steele and Laszlo Sakay in 2002. They looked at this 4-taxon scenario again, where they had length x for the internal edge and y for all the pending branches. And they observed that the number of characters needed to reconstruct the true tree grows at a rate of 1 over x squared. So basically, the longer or the shorter this edge gets, then the more characters you need to reconstruct the tree, and that's at a rate of x squared, where x was the length of this internal branch. But the question really is, what happens if we do something like what Ziheng Yang basically did in his simulations? We keep sort of the ratio of the length of the pending branch and the internal branch fixed, and then take the value of the internal branch that minimizes the sequence length needed. So sort of the best possible case. What happens then? And I and Mike tried to do this in 2009, and we did it for the two-state symmetric model. So we only had states A and B, and going back and forth is sort of the same probability. That's why it's called symmetric. And so in our case, as I said, we wanted to keep the ratio between the interior and the pending branches fixed. So we had the pending branches of some length multiple of the internal branch. So P is just some number more than 1. Then we figured that the sequence length needed to reliably reconstruct the true tree, where reliably means with some given probability 1 minus epsilon for some epsilon, grows at a rate of p squared. So as p grows, which is more or less equivalent to x getting smaller in the relation, then we need rate of p squared number of characters to sort of reconstruct the true tree. However, as I said, the very first approaches I showed you were based on simulations, and now the others, they employ only 2 states. Well, oops, that's not really interesting for biologists. Normally they at least look at 4 states when they talk about the DNA, for example. So what was still needed was a mathematical analysis of the influence of branch lengths on tree reconstruction for 4 states. And this is now what I looked at with Marta. And so this is then just the Jukes-Cantor model that is basically familiar to all of you, I guess. So we have 4 states now, and we also looked at the same tree as before. And yeah, and before, I should mention maybe, before we could actually start to do anything, we had to apologize to our friend Miss Parsimony, because we criticized her in the past a lot and sort of threw her out of our work, but now we have to remorsefully offer her an assistant position in our current project. I will show you why that is in a minute. So it's not only Marta and me, it's Marta and me and Miss Parsimony who then solved the following. So it turned out that for a reliable maximum parsimony reconstruction, now just for a moment, just looking at parsimony, the sequence length needed still grows at a rate of p squared. And for the optimal value of the internal branch length, this rate of p squared can be obtained. Okay, so it's a tight bound. So for 4 states, actually everything is as great as for 2 states. So this made my friend Miss Parsimony really, really happy. Okay, just because there are many mathematicians here, just a short idea of the proof. So, what's that? Okay, I don't know, it messed up my slide a little bit. So basically what we did is we introduced a random variable which assumes value 1 if the it's xi, if the ith character in our alignment is of the kind alpha alpha beta beta, and -1 if it's alpha beta alpha beta. So it's 1 if the first tree is supported, and -1 if the second tree is supported, and 0 else. And then we introduce the sum, another random variable, which is the sum of the first k such random variables. And the nice thing here is that we can do this. So note that this sum here will be larger than 0 if and only if the first tree is favored over the second tree. And we can do the same thing basically for the first tree being favored over the third tree. So the nice thing then for this sum is that if we assume that these xi are IID, then by the central limit theorem or some variation of it, basically this sum is normally distributed. And yeah, note that this just says something, this zk says something about T1 being better than T2, but we can do the same thing for T3 as well. And the nice thing here is, and that's also why it's maybe not so surprising that it works for 4 states just as it does for 2 states, that the only parsimoniously informative characters on on 4 taxa employ 2 states. Okay, so we didn't even have to take care of any extra things here. Okay, and so we had Z being normally distributed with a mean and variance or standard deviation here, and these only depend on the probabilities that our x1, we can say, because they are IID anyways, equals 1 or x1 equals -1. And these probabilities can then be easily calculated, so can just use the Felsenstein algorithm or whatever. With Mike, I did it with the Hadamard transform, and Martha prefers the Fourier transform because she likes things complicated. But in the end, you end up with such nice probabilities which only depend on x and p. So only the edge length of the internal edge and the factor you need for the pending branches. And in the end, this enabled us to use the ratio of mu k over sigma k to find a value of x that minimizes k, where k was the number of characters needed. Okay, so for maximum parsimony, we now know that the number of characters needed to reliably reconstruct the true tree grows at a rate of p squared. However, there are still the other guys here, Miss Distance Based and Mr. Likelihood, who like to attack Miss Parsimony, right? We all know that, she's statistically not consistent and so on. And so the question is, can they do better? For instance, can they do it at a rate p? And the answer to this question is no, they actually cannot. And this can be shown using the so-called Hellinger distance. So basically, no method can do better than that here. Okay, so in this case, Miss Parsimony can shoot back, and she wins. And that's also the reason why we employed her here, because parsimony is a really nice method that can be analyzed combinatorially. And in the end, we knew that if we would get it for parsimony, it couldn't be done any better anyways. Okay, so the outlook is, and we are working on that at the moment, just that with that baby of Martha in the meantime, we are a bit delayed with the research now. So what happens if we approach the Felsenstein zone? So what happens if we let 2 of the pending branches on each clade, if we let them grow? And what happens in general with different tree shapes or more taxa? So what we are aiming at is like sort of an overview as Ziheng Yang give it for his simulations. We want to give that analytically. Okay, that's it.
Right, that's very timely. There's time for a few questions if anyone has.
Okay, so you're looking at the point where the case where the point estimate is getting the correct tree back. But a lot of the time, Bolus is interested in the fact that you're able to reject the other 2 trees in the confidence interval. So it's your bootstrap proportions 10 to 1, rather than just a point estimate 10 to the correct tree. Have you got any idea about how quickly data gives you data allows you to tend to a very high confidence in the true tree?
No, we haven't actually looked at that yet, but that would be another question that's definitely of interest in this context. Yeah, thanks for this suggestion.
Okay.
You said that a non-parsoning method cannot do better than parsoning, but can they do as well?
Well, I mean, there's always, for instance, likelihood with no common mechanism, which does the same thing that parsimony does. Then the answer would be yes. I don't know. I would think so. I would think so. But I mean, it's not as easy to analyze this in the setting like with parsimony. But I would assume so. Yes.
Okay, let's thank Mareike again.